Good afternoon, students. So, welcome to our online session. So, in digital signal processing and application, as you know, I'm going to teach you about Dspa subject for EEE 6th semester. In today's session, we are going to see in details about it how the signal ends at its function by using the discrete Fourier transform and inverse discrete Fourier transform can be going to function. And we are going to see the twiddle factor as well, how the twiddle factor is going to be work for that, and based upon that we are going to work on the functionality. The main concept of R is how the DFT and IDFT is going to use a twiddle factor for 4.8 point. We are going to see in that, and even though we are going to understand what are the application part of it and how we are going to apply that concepts by using discrete Fourier transform, inverse discrete Fourier transform and fast Fourier transform. So these are the concepts we are going to see that one, right? So now in today's session I am going to teach you about that. And before proceeding ahead, just take a brief overview of a previous session, what we discussed in the previous session. In previous session we talk about the DFT and IDFT, the difference of DFT and IDFT, and we are talk about the functions of it, how the twiddle factor is going to be used for DFT as well as for IDFT. Okay, so that concepts we already covered, and now in today's sessions we are going to learn more about it, DFT and IDFT, and then we are going to learn about the functionality of that function, how we can use for that by converting n domain signal into k domain signal, because in DFT you are converting n to k domain, right? For IFFT, for IDFT we are converting k domain into n domain. What about FT actually? For a transform we are converting n domain into frequency domain signal. So this part we already have covered. And now in today's session we are going to learn about it, how we are going to function by using these functions. So we are going to see that one as well, the functionality of it, and how we are going to use for that particular functions also we are going to cover in today's session. Okay, so let us proceed with that concepts and how we are going to use that one also we are going to see in our today's session. So students, so we are going to see about the DFT properties. In the previous session also we have talked about the properties of it. So we have talked about the symmetric property. What is symmetric? It is depends upon 4 points. One is symmetrical property to real wide loop function. If only if you get real parts is there is no imaginary part, then this is called symmetric property for real function. A real and even means only imaginary part should be 0, and the imaginary part of that domain if you convert that is also 0. If both the function for n domain imaginary part is 0, for k domain also 0, then that kind of function is considered to be the real and even sequence, right? For the same real and odd sequence, reverse of it. So xi of n is equal to 0 and xr of k is equal to 0. Real part of k domain and imaginary part of n domain both are 0, then we can say real and odd function. And for pure imaginary function, what we can say, x of n, that is xr of n is equal to 0, then we can consider as it is a pure imaginary function. This is the functions we have talked about in the previous session also. In today's session we are going to learn in detail about it further, what are the things we are going to learn it, and how this properties is used for the DFT, that is also we are going to understand and we are going to work on that. Okay, so those concepts we are going to cover in today's sessions, and we are going to see the further concepts what actually we do have for this particular DFT and IDFT. All those concepts we are going to cover in today's session. Okay, so we proceed with those sequence, with those particular functions, how it is going to work on it, and what are the parameters, it depends on that. If you do have even and odd functions, how do we segregate those functions, we are going to learn about it in today's sessions. So as you can see here students, so linear and circular convolution, this is an important question. So basically we know about linear convolution. How do we find the convolution? Basically, so when we had one function into another function, when one function is convolved with another function, we try to take a delay of that, we try to find delay of that particular function, and we try to find the solution of it. That can be done by using matrix approach, by using graphical approach, by using the circle concentric circular method that is used for circular convolution, and matrix method also we are used for circular convolution. Likewise we are going to use those particular functions. Okay, so that is also we are going to see in today's session. So basically what is the linear convolution is all about, students? The linear convolution, how can you find the linear convolution? You can find by considering two sequence. Suppose you do have one sequence x of n, another sequence x y h of n, that is impulse response. You want to get the output of it. How do we get the output? To get the output, we'll write x of n impulse response of h of n, that can be given by the same output. Output is y of n, that can be calculated by using this linear convolution. What about circular convolution? Circular convolution is nothing but the multiplication of two DFTs is called as circular convolution. Whenever we try to find the DFT of two response, when you see that one, when it is forming that one, then we can find the circular convolution for that given sequence. Then multiplication of two sequence in time domain is called linear convolution. If you're using in time domain, students, if you're multiplying two sequence, then it is called linear convolution. What about circular convolution? Multiplication of two sequence in frequency domain. If you see the frequency domain, if you try to multiply the two sequence, then we consider that as a circular convolution. So linear convolution formula is what? Linear convolution is given by the equation y of n is equals to x of n convolves with h of n, right? Whereas circular convolution is written as y of m is equals to. So students, so we see these signals. Now we are proceeding with the circular convolution. In the circular convolution, we had first sequence x1 of n is converting into x of k, x2 of n is converting into x2 of k. If you want to mention the circular convolution, we can write in this form: x1 of n, n circular convolves with x2 of n. The DFT of that we are applying and we are converting it to x1 of k into x2 of k. Okay. In general, we can write that formula in this way: y of m is equals to summation n is equals to 0 to n minus 1 x1 of n into x2 of m minus n, right? So this is the way we can represent the signal whenever we try to find the circular convolution, right? In the block diagram form, since the multiplication of two sequence in time domain is called linear convolution, if you are doing in time domain, that is considered to be the linear convolution. Whereas if you're doing multiplication of that two sequence in the frequency domain, then that particular part is considered to be the circular convolution. So difference of these both functions is what? One is done in the time domain, another is done in the frequency domain. So when we are doing in the time domain, then it is the what? Linear convolution. When you're doing in the frequency domain, then it is becomes circular convolution. As you can see in the diagram, when you have DFT of first sequence x1 of n, actually it has to represent here, so that is x of k. If you are multiplying with second sequence h of k, though both we multiplied, if you apply that IDFT, then we can get x1 of n convolves with h1 of n, right? This is the convolution, right? The result of both are totally different but are related with each other. So that is what relation between these two. So there are two methods as used to calculate the circular convolution. One is the graphical representation form, then the matrix approach. So these are the two methods we are using to find the convolution of it. So basically, students, you should know the difference of both. So in linear convolution, what we are doing, students, so we are taking the signal, two signals which are x of n and h of n. We try to find the response of this, and output would be y of n. Here we are using 2 DFT is called circular convolution. When you multiply 2 DFT, that is called it as circular convolution. So multiplication of two sequence in time domain is linear convolution, whereas in frequency domain it is what? Circular convolution. Just now I have explained that particular point. Linear convolution is given by the equation y of n is equals to x1 of n convolves with h of n. The circular convolution is calculated as y of m is equals to summation n is equals to 0 to n minus 1 x1 of n x2 of m minus n we can represent. Okay, so y of n we wrote it, and y of n for the sequence in n domain. Here we are writing in frequency domain. We write the functions. The linear convolution of two signal returns n minus 1 elements, where n is the sum of elements in both the sequence. Whenever we do have n means both the sequence needs to be same. Number of samples in the first sequence and the number of samples in the second sequence must be equal, so as to perform the linear convolution. That's the reason here mentioned n is the number of sample which is the sum of first sequence n1 plus second sequence n2. If you add both of them, then how many steps it is required to perform it? N minus 1. Suppose first sequence is 4, second sequence is also 4, like 1 1 1 1 1 1 1 2. If you do have these two sequence, suppose I just take this example here. See, 1 2 3 4, there are 4 sequence here, again there are another 4 sequence, right? Total how many? n1 plus n2, 4 plus 4, 8. So how many steps is required? 8 minus 1, that is 7 steps is required to. So students, so we proceed with the multiplication of the two sequence, which is a part of our concepts we do have in the linear and circular convolution. So we are proceeding first thing with the circular convolution. In that, what actually we are using the multiplication. If you do have first sequence x1 of n and we are multiplying with that DFT with n samples, we can write as x1 of k. If you do have second sequence x2 of n, if you're multiplying with DFT, if you want to find the transformation of DFT, then it will become x2 of k. So that multiplication will become what actually? It's 1 by n x1 of k and convolves with x2 of k. This means that multiplication of two sequence in the time domain results in circular convolution of their DFT in frequency domain. Okay. Similarly, if you want to find the time reversal of a sequence x of n, that can be written as x of k. Then if you do have x of m minus n, means you want to find the reversal of time. You want to fold that sequence. So to do that one, what actually we are using? We are using x of minus n. We try to find DFT of that can be written as x of capital N minus k. That means small n we are converting into capital K. Right? That is means n domain we are converting to k domain. That is called as property of your circular folded. So it means the sequence is circularly folded. Its DFT is also circularly folded. Next part is nothing but circular time shift. How do we apply the time shifting? Time shifting, if you want to do it, the circular time shift state that if x1 of n discrete Fourier transform, if you want to write as x of k and x of n minus 1, as you can see here students. So what actually it is n minus 1 of small n, capital N, that is nothing but a number of samples. If you want to write that DFT of it, x of k into e power minus j 2 pi k n by n, right? So this is what we are converting into x of k. It's written here, it's went to that point, but it is come under that point only. Okay, that means what is the conclusion for this? Therefore the shifting of the sequence circularly by I samples is equivalent to the multiplying its DFT by twiddle factor, that is e power minus j 2 pi capital K L by n, right? What is that? Nothing but n, whatever the values we do have, number of samples, we apply that and we try to write that particular sequence and we try to write the output of that sequence. Similarly, when you proceed with the property of that, the sequence of circular convolution, we have till now finished students. We have covered. So students, so we just want to see the complex conjugate property. In that, what actually we are seeing, x of n we are converting into x of k, x conjugate of n we are writing as h conjugate of minus k with n, right? With what is the small n indicates for the circular convolution, right? If you do want to write the conjugate of it, if you do have a z value, suppose that is equals to x plus jy, if you want to write that in terms of x minus jy, that is called it as complex conjugate z bar. Similarly here also we mentioned x conjugate of n, s asterisk of n is nothing but s asterisk of minus k, s asterisk of n minus k, capital N minus capital K. Similarly, if you add x asterisk of minus n, that is nothing but x asterisk of n minus k, that can be written as x asterisk of k, reverse. If you add n here, we do write n minus k. If you do have here n minus k, we write as k. Similarly, we proceed with the next property. This property clear? So in that, what actually the main concept in this complex conjugate property, you need to understand that how it is going to work on that. Next is circular correlation. Correlation is the name itself. Correlation means there are two types of it. One we have learned about auto and cross. Here as you can see there, the formula is for cross. R of x of y. One is x sequence, another is y sequence of L. We can write as capital Rx of k. So this is what x of k, y of asterisk of k, where small rx of gamma of xy of L is nothing but the circular cross correlation, which is given by this formula. You already have discussed about it when we talk about the correlation, autocorrelation, cross correlation, the properties of it, how it is going to work on it, difference of convolution correlations, everything. We talk about those concepts in the previous session as well. Next, we are proceeding with the Parseval's theorem, students. So basically, what is the Parseval's theorem? The Parseval's theorem is used to convert your given sequence for the energy and for power sequence. We have learned about it, right? So what is the definition for our convolution here? So summation n is equals to 0 to n minus 1 x of n y complex conjugate of n, that can be written as 1 by n summation n is equals to 0 to n minus 1 x of k y conjugate of k. So this equation gives the energy of first finite duration sequence in terms of its frequency component. So this is the one of the sequence we do have in a Parseval theorem. So this about the all properties, students. We have learned all the properties of your circular convolution, starting from the multiplication, talking about the folding and everything we just learn in details of it, how it's there for all the DFT concepts. So starting from first linearity, then we talk about the properties of your folding, then we talk about the properties of symmetricity, and we talk about all the properties in the previous class session as well as this class session. So what is we have learned, take a quick recap. First we talk about periodicity, n plus n, small x of n, x of k plus n is nothing but x of k. This is what periodicity property of DFT. Definitely you will be going to get the question based upon the properties of your discrete Fourier transform to prove it or to give a statement for it. So that is very important. You need to understand and you need to note it down, all the properties separately. So first in periodicity, we have seen that formula as well in the previous class. In linearity, what we have learned, if your first sequence x of 1 of n, if you take d of t, it will become x1 of k, x2 of n, it will become x2 of k. If you take constant factor a1 x1 of n plus a2 x2 of n, that will be written as a1 x1 of k plus x2 x2 of k. Next we learn about circular symmetricity of a sequence. So it depends upon 4 conditions. First condition is x of n minus n is equals to x of n, x of capital N minus n is equals to x of minus of x of n. This is even, this is odd, right? So if you're getting the circular folded for that we can write in this format. That is x of minus of capital N is equals to x of capital N minus small n. This is called circularly folded. Likewise, if you take the anti-clockwise direction, give delay sequence. If you take a clockwise, you should advance the sequence. Means x of n minus n for delayed, x of n plus n for advance. Likewise, fourth property we talk about symmetricity property, that depends upon 4 parameters. First parameter is symmetric and even. So what is the symmetric properties or real valued function? Imaginary term is 0, then it is symmetrical. Real and even means imaginary term for n domain and for k domain, both are 0, real as well as even, right? Real means this condition. Even means all terms, if you transform also, if you are not getting any imaginary term, then real and even. What about real even term value for that student? From e power j theta cos theta minus j sin theta. Real term is cos theta, right? J sin theta is an imaginary term. So we use cos theta to find out that particular function. Next is real and odd functions or odd sequence. For that what we can write? If you take a real means xi of n is equals to 0. For odd, your real part needs to be 0, right? For odd functions we'll write x r of k is equals to 0. So both if you combine it is this is the sequence. So for odd sequence what we'll get? Only we'll get the imaginary term. So minus j sin theta. Theta is nothing but by using the twiddle factor e power minus j 2 pi k n by n. So that's the reason we write 2 pi k small n by capital N. Next property we will learn about in that only. The fourth condition is pure imaginary x of n. That is, if real part is 0, then it is completely imaginary. So real part of k is sin theta will write, imaginary part of k will write as cos theta, reverse of it. Next we talk about the circular convolution. In circular convolution we have seen, if you represent this circular form, circle x1 of n, circle with x2 of n, we are multiplying these two sequence. So another name for this is multiplication in frequency domain. That is called circular convolution only. So we have seen the difference of linear and circular. So linear is what? It is just to find the convolution of the sequence, and it is a multiplication of two sequence in the time domain. One must be impulse response must be there, whereas the circular convolution is for multiplication of two sequence which should be circularly convoluted. And linear convolution always is a frequency domain, time domain, and the circular convolution is frequency domain. The formulas for both is here, right? Here x of k, h of n minus k, from both the sides k is equals to minus infinity to plus infinity. Infinite number of samples we can take, whereas here it needs to be finite. And x1 of n, x2 of m minus n of n, that n indicates a circular convolution. Here in both the sequence, what we call the number of samples must be same. For circular it is not mandatory, and the total combination for that would be the output is n minus 1. So this is how we talk about the properties for that. And next we proceed with the next property is what? Multiplication of two sequence, then circular time shift, then circular frequency shift. For that, how time shift and frequency differ from each other. Here e power minus j 2 pi k n by n will multiply with the x of k for circular time shift. What about the frequency shift? In the frequency starting only will multiply, that is x of k n e power instead of minus j will take it as plus j, e power plus j 2 pi k n k l, we are taking some other factor as l n by n, right? This is called circular frequency shift. Similarly, complex conjugate property. Complex conjugate means if you had z is equals to x plus iy, z bar is x minus iy. in a general form will represent the complex form. Whereas for complex conjugate of R sequence, we are what we are writing in that, we are writing as x of n is nothing but x of k. If you take the x conjugate, x asterisk of n is nothing but x asterisk of n minus k. We're putting the delayed and we are proceeding ahead. This is for complex conjugate property. If you are taking the n domain, we are converting into k domain. If you are taking initially only the k domain, that needs to be written here x asterisk of k. Clear? So this is nothing but small n, right? That we are writing as k domain function. So this is the way we can write here. Instead of, actually it has to be capital N minus small n, students. So this is a mistake in that formula. You properly note it down. So instead of minus n here is there, it should be minus n minus small n. Here as you had n minus k, right? Similarly here capital N minus small n needs to be there. Clear? Next we do have a circular correlation property, and we have talked about the correlation is there are two types, auto and cross. Here we are considering the cross correlation functions. We are taking that cross complex property for that, and Rx of y is equals to, with the functions we are taking Rx of y with that functions, and we try to write the output for that particular function by considering these two responses. Okay, so that two responses we are writing, and we try to write the output for that, and that can be written in this two format, x of n and x of. So student, that's about the Parseval theorem property, and then we are proceeding with the property. What else we do have? So till now we talk about till 12 properties, right? So those we covered in today's sessions. So basically you need to understand all the properties, and you need to maintain the notes for all the properties and note it down in somewhere, so that it will become easy for you to note it down. And for the future reference, I'll just now said that it is important even for the external exam and even for the internal as well. So for both the things you need to maintain the notes. So that's it about today's sessions. Thank you very much. In the next session we are going to learn about the application of DFT, where the DFT is going to be used, and what are the methods to apply for linear filtering, as we talk about the FIR filter and IR, right? FIR stands for finite impulse response, IR is nothing but infinite impulse response. We are going to, for that particular part also, before that we are going to learn these concepts. What are those concepts? The FFT, butterfly diagrams, how the butterfly diagrams can be used to find out the response, how we take that functions, how we draw the diagram basically. So that we are going to see. These are the concepts. Just I want to take a brief introduction so that you should know what idea we are learning and what are the things it is essential for you to understand for the further classes, right? So this is about the today's session. So maintain the notes and try to write all the things at one end. Thank you very much. Be safe. Have a good day.